These towers are designed to move. High above Manhattan, some of the world's most expensive apartments gently sway in the wind. On certain days, residents may hear walls creak, doors shift, and water move inside their pools. Yet this movement does not necessarily mean the building is unsafe. In fact, engineers expect it. So why would anyone design a billion-dollar skyscraper to move? And how do they stop that movement from becoming unbearable? The story begins with a simple problem. Land in central Manhattan is extraordinarily expensive. Developers cannot make the site wider, but they can buy unused development rights from neighboring properties and move that potential floor area upward. The result is a new kind of residential skyscraper, often called a pencil tower. Unlike an office tower, which needs large floors for hundreds of workers, a luxury residential tower can survive on a remarkably small footprint. A single apartment may occupy an entire level, with uninterrupted views in every direction. That exclusivity turns height itself into a product. The higher the apartment, the more dramatic the view, and often the higher the price. Along the southern edge of Central Park, this logic created what became known as Billionaires Row. Towers such as 432 Park Avenue, Central Park Tower, and 111 West 57th Street transformed the skyline. But making a building tall is only half of the challenge. Making a very tall building extremely narrow changes the way it behaves. Gravity is still important, but as the tower rises, wind becomes one of the forces that controls almost every major design decision. Wind does not push a skyscraper with one perfectly steady force. Air separates as it moves around the edges, creating alternating vortices behind the building. These swirling pockets of pressure can pull the tower from side to side. If their rhythm approaches the natural frequency of the structure, the motion can become more noticeable. A broad office tower has more width and usually more stiffness to resist this effect. A pencil tower has far less width relative to its height, so controlling acceleration becomes crucial. Engineers are not only asking whether the concrete and steel will remain strong, they are also asking whether a person drinking coffee on the 80th floor will feel comfortable. Human beings can detect surprisingly small accelerations, especially when the movement is slow and there are no visual clues explaining it. The tower might be structurally safe while occupants still feel dizzy or anxious. That creates two different design limits: strength and comfort. Strength prevents collapse or permanent damage. Comfort limits how much motion residents experience during winds that may happen every year. For ultra-luxury apartments, passing the structural calculation is not enough. A home priced in the tens of millions of dollars is also expected to feel calm. The clearest example is 432 Park Avenue. Its square tower rises about 15 times as high as it is wide, giving it proportions that would once have seemed extreme. From a distance, the facade looks almost simple: a regular grid of square openings repeated into the sky. Structurally, however, that simplicity hides an elaborate system. The reinforced concrete core works with the stiff exterior frame, while outrigger levels help connect different parts of the structure so they resist lateral movement together. At carefully chosen intervals, two-story mechanical levels are left open to the wind. These openings are not unfinished floors. They are part of the aerodynamic strategy. Allowing air to pass through the tower disrupts the organized vortices that would otherwise form around its sides. Think of the difference between pushing a solid sail and pushing one with controlled openings. The wind still acts on the building, but the pattern becomes less efficient at driving repeated motion. Engineers tested the tower using models and wind studies before construction, adjusting its structural behavior and damping systems. The goal was never to make the building perfectly motionless. That would require enormous amounts of material and could be economically unrealistic. The goal was to keep movement controlled, predictable, and comfortable. Aerodynamics alone cannot remove every uncomfortable movement, so engineers add another tool near the top of the tower: the tuned mass damper. A damper is essentially an enormous moving weight designed to respond out of phase with the building. When wind pushes the tower in one direction, the damper's motion helps oppose that response and dissipate energy. At 432 Park Avenue, two dampers weighing roughly 600 tons each were installed high in the building. Central Park Tower uses a similarly specialized system designed for a tower that rises more than 1,500 feet and includes significant cantilevers. The exact form can vary. Some systems use a suspended steel or concrete mass, while others use liquid moving inside tanks. But the principle is comparable: Add a controlled secondary motion to reduce the motion people feel in occupied spaces. The damper does not hold the skyscraper rigid like a giant anchor. Instead, it changes the dynamic response of the structure. This distinction matters. Skyscrapers are already elastic. Concrete compresses, steel stretches, and the entire frame responds to changing loads. A small amount of flexibility can prevent forces from concentrating destructively. Good engineering does not eliminate movement. It manages movement, much like a suspension system manages the motion of a car rather than attempting to make the car completely rigid. A few blocks away, 111 West 57th Street pushes slenderness even further. Commonly called Steinway Tower, it rises from a narrow site beside the historic Steinway Hall and reaches a height-to-width ratio of roughly 24:1. That makes it one of the most slender skyscrapers ever constructed. Its form is not simply a smooth rectangle. The tower steps back as it rises, creating a dramatic sequence of setbacks on the southern side, while a more continuous facade faces Central Park. These changes shape both the architecture and the wind response. The structure relies on a powerful concrete core and perimeter elements working together, while a large tuned mass damper near the top helps control acceleration. Central Park Tower uses a different silhouette again, with setbacks, notched corners, and upper floors extending over a neighboring property through a cantilever. Each tower is responding to a unique combination of site boundaries, zoning rights, apartment layouts, structure, and wind. This is why copying the appearance of a pencil tower is not enough. Two buildings of similar height can experience very different wind patterns depending on their width, orientation, neighboring buildings, and even the shape of their corners. Engineers therefore test models in simulated winds approaching from many directions, not just one dramatic storm scenario. So what does a resident actually experience? Usually, nothing dramatic. The movement of a well-designed tower is far smaller and slower than the exaggerated bending shown in animations. During stronger winds, however, subtle motion may reveal itself indirectly. Hanging lights can move, water can shift, and building components can make noise as different materials respond. Elevators, plumbing, partitions, and door hardware must all tolerate a structure that is never perfectly still. This is where headlines can become misleading. Reports of creaking, leaks, elevator problems, or disputes inside a tower do not automatically prove that its main structure is close to failure. A skyscraper is a collection of thousands of systems, and an operational defect is different from a collapse mechanism. At the same time, dismissing residents' experiences would also be a mistake. Comfort is a real performance requirement, especially in a luxury building. If motion causes noise, disrupts an elevator, or makes an apartment unpleasant during common wind conditions, the owner may reasonably consider that a serious problem even when the structural frame remains safe. The more ambitious the building, the more coordination it demands between structural engineers, architects, facade specialists, mechanical designers, contractors, and operators. The tower may be a structural success while still exposing weaknesses in construction quality or building management. The engineering is only one part of the controversy. Pencil towers also reveal how zoning and global wealth reshape a city. By combining development rights and concentrating floor area into a narrow footprint, a developer can produce a relatively small number of extremely valuable homes with extraordinary views. Supporters see this as technical creativity. Private investment paying for ambitious architecture on some of the world's most difficult sites. Critics see vertical safe deposit boxes, apartments purchased as assets and used only occasionally, casting long shadows while doing little to address ordinary housing needs. Both interpretations can exist at the same time. The towers are genuine engineering achievements, but their form is inseparable from the economics that made them possible. Their narrow floors are not simply an aesthetic preference. They are the physical expression of land prices, air rights, exclusivity, and the premium attached to an unobstructed view of Central Park. This also explains why similar towers do not appear everywhere. The market must support enormous design and construction costs. The planning rules must allow height to be assembled, and buyers must value the result. Without all three conditions, the same structural technology might be possible, but financially pointless. Billionaires Row is therefore not just a skyline. It is a diagram of New York's property system drawn at full scale. Are these towers too tall or too thin? From a structural point of view, slenderness is not a single forbidden number. It is a design condition that demands increasingly sophisticated analysis, stiffness, damping, testing, and quality control. A tower with a ratio of 24:1 can be engineered successfully, while a much wider building can perform poorly if its systems are badly designed or constructed. The more useful question is whether the entire building meets the level of safety, comfort, durability, and public value expected from it. New materials, better simulation, real-time sensors, and improved damping technology will make even more ambitious structures possible. Sensors can compare predicted movement with the tower's actual response, allowing engineers and operators to identify unusual behavior over time. But technology does not erase the trade-offs. Extra structure consumes material. Dampers occupy valuable space. Open mechanical floors affect the architecture, and every additional meter of height increases demands on elevators, plumbing, construction logistics, maintenance, and emergency planning. New York's pencil towers are designed to move because controlled flexibility is part of how they survive. Their greatest achievement is not that they defeat the wind, but that they negotiate with it. The next time one of these impossibly thin towers appears to stand perfectly still above Manhattan, remember, hidden inside, thousands of tons of structure are responding, dampers are moving, and the entire building is quietly adapting to the air around it.